You think I should go first to keep with the theme of the graphical interface rather than jumping back and forth?
Sure.
Okay. I hear your response, Kristen, to my earlier comments that, yeah, it's an integrated package, and I understand that. And that's the goal here is to really create a set of tools that can function together. So my role has been to see how we can use the NeuralGlancer viewer. We know we want to use that technology and integrate that with these other technologies. I think at first it wasn't totally clear if this was going to be more an extension of the existing graphical interface or a web-based thing. And I think as time has gone on, we see that we really want to just have a web-based technology that maybe is completely divorced from the existing graphical interface. Just talking about the alignment tool right now. So
I think what we're looking for is to completely remove Qt entirely from the software and replace it with NeuralGlancer.
Yes,
that's the idea.
So kind of separate out Art's Swift IR algorithm and plug that into something that's like a web-based technology. So one thing, so a very key step that has to be taken to use the NeuralGlancer viewer is that we have to have the data set, which is a stack of TIFF images in a format that NeuralGlancer can recognize and know what to do with. So there's a few options. NeuralGlancer has its own format called pre-computed. And then there's different container technologies. So a container is going to let you put the images into this container, and it's literally a directory you can CD into from the command line, and you interact with it like it's a directory, but it's got metadata associated with it. The metadata can contain information about the project, or whatever we want it to. It can have like the scale, and so this is going to be a dot. There's several of them, like a .zattrs is going to be the Z attributes file. So each bucket's going to have one of those, and so that's one benefit, is that you have this metadata associated with the the container of your images. But I don't know why I led with that, because that's maybe like the least cool thing that containers can do. So with a container, it's also going to take care of the chunking. It's going to compress based on the compressor that you specify. And we did a little bit of benchmarking that I'll show with which compressors to use and which one's the fastest. This is benchmarking the read and write performance of writing your images and copying your images into this container. So the great thing about containers, so there's like so many great things. So there's the that you can have metadata, and that works well. There's the fact that it does compression, it does the chunking, and that's all sort of invisible and behind the scenes. It really makes that easy. There's one thing, it also, the containers know how to work with groups of images. So this provides for the scale hierarchy. So that functionality is all kind of built in. You don't have to think about what each scale of the image is doing as we're trying to align them. Like all of the scales are in the alignment. So our plan is to have all of the images, the very first step before alignment is to put these images into a container. The container that we've been working with is a new technology called SAR. I'll go back to that.
Joel.
Yes.
So it sounds like this is redundant. I mean, the metadata, Kristen keeps it in an Excel file, and so this, you're saying it will obviate her Excel?
Well, the metadata is also accessible from the command line, so we can write code around the attributes file. So we can work with objects.
Josh, what type of metadata are you talking about? What do you mean, like animal numbers?
it could be anything, but the most obvious thing would be the scale, like the resolution, and that.
You're talking about
Yeah,
the
I can see
image
it.
metadata. What Terry sees as metadata and what I usually see as metadata is all the physiology associated with the experiment, the animal's birth date.
Yeah, that could be in there, but that's not really along. I'm thinking more the technical, like kind of like an image has like the EXIF data. I'm kind of thinking as an analogy, like, but to go with the technical.
So is it constrained to be only about the technical details of the image? I'm saying that this might be an opportunity to actually put animal data into it too. I mean, so that you could keep track of it. So it's, it's connected. It's, you open it up, where the data is from, what the conditions were.
Yeah, that's a good
Normally
question.
we're blind as to
And
condition, Terry.
You're
Not
asking
all
him to use-
If you can blind it too, but the point is though that there's a link somewhere.
Yeah.
You can
Well,
get-
I think, Terry, your idea of having let me tell you that it's very hard to get people to enter metadata into a thing after they've already collected it someplace else. So the metadata gets collected, like if Olga's starting her physiology experiment, she'll put into that software all the information about the animal. And so, there'd have to be linking back to other software that would hold that kind of data. It's not a bad idea, but it might be all you'd want to do initially is have a link, as you say, to where that data resides, so that it doesn't have to be entered more than once.
Yeah. No, that would be more efficient. Yeah.
So yeah, it's a powerful opportunity. I agree. It hasn't been at the top of my mind what all we can do with the metadata, but I'm glad you see it as a useful opportunity because it's all anything that's in the metadata or the attributes file is good. So let me show you right here an example.
Another question. I have another question, which is, could these containers then be imported into the cloud?
Yes. So yeah, once they're in the container, that's another great thing, having them in a container. It makes them very portable to the cloud. And NeuroGlancer has several different ways that you can interface with different clouds, Amazon or however you want to do that. There's a few different integrations. So I just wanted to show you a very simple attributes file. Let me fix the formatting here. It's all center aligned.
This looks like an upside down Christmas tree.
Okay.
At least it's not red and green, Terry. The whole last paper I was discussing with Matt Kennedy, not Mary Kennedy, that we're working on. The color scheme is red and green.
You should tell Tom, warn Tom, right?
We checked it to be sure a protenope or a deuteranope can see it, but the protonopes are not going to be able to see it at all.
Yeah. Depends on the shade of red and green, I think. To me, it depends on the shade of red and green.
You guys can use me as a guinea pig. I believe I'm a deuteranope.
Yeah.
So I'm a tritanope.
Oh, boy.
So anyways, this is just a very simple attributes file. So yeah, to quickly recap, so we got the metadata, the container is going to chunk the data for us. It's going to compress the data for us based on the compressor that we assign. It's going to be very portable. So it's got all these great things. So we've done that. And I'm just kind of expecting you guys to like see this slide. I'm not going to read it to you. But these are the two things. So we want to get the data in this format, and then we want to set up the viewer. And what I'm going to show you today is a script that it does all of these things. It's just a script that's just jam-packed with all of these. It just does all of these things all in one script. It shouldn't be in one script. I mean, this should be modular, but that's just for demonstration purposes.
So Joel, a quick question for Joel and Tom.
Yeah.
I noticed how this new efforts is gonna help for the Reconstruct Plus. Also, and change the Reconstruct, the older Reconstruct. How much you are changing NeuroGlancer, or what aspect of NeuroGlancer you want to tweak or change or improve?
So NeuroGlancer has a class called a viewer. So neuroglancer.viewer, if you go into the GitHub repo for it, you can see all what it can do. But a viewer has a lot of so a viewer can have each viewer class, once it's instantiated, it has a state, and you can start changing things about the state, like whether it's the color of the background or the scales, and you start acting on the state, and the viewer is instantiated within a server that's serving it. And it's so what we're going to be doing, what I'm going to be showing you today is just where we've got the so NeuroGlancer we're using the Python API of NeuroGlancer, and that's installed on my computer. And we're going to start a local web server on localhost, and then we're going to tell it where to look on my hard drive. And then it's, since we've started a local server, it's the NeuroGlancer API, Python API is going to take care of the rest of the work to create a NeuroGlancer view, like you just saw Shweta demonstrate. Did I answer your question?
Well, yeah, but my point was that during the whole project, what aspect of NeuroGlancer you want to change? Do you want to modify it, and what aspects of it you want to change?
So we want to use it
I
as
think Tom has some plan for NeuroGlancer.
So
as
have
well.
you used the alignEM-SWiFT? Are you familiar with it?
No, I know it's the.
So that's gonna basically. You can see three window panes. There's the reference image, the base image, and the aligned. And you
have a picture of it on the previous slide. You have a picture of that on the previous slide.
Yeah. So we want to get this sort of within. We want to do this within NeuroGlancer, and then we also want to have the 3D reconstruction also in there.
Yeah, very good.
So,
thank you so much.
Yeah.
Good.
And NeuroGlancer is customizable to be able to do anything you want.
Yeah, it's got a great API.
All you have to do is write the code to customize it.
Yeah, custom.
Yeah, and Jeremy, the guy at Google, who this is his sort of project, so this is his thing, and he's very responsive and somebody that we can work with. So, all right, so I've already kind of explained this, so I'm going to go to the next slide. Yeah, so previously we were just acting on a raw image stack, but we're going to use this container. More about containers, as I was saying. Containers enable data chunking, data compression. Containers are designed to handle image scale pyramids. The terminology for that in container vernacular is groups of images. NeuroGlancer has built-in support for several container types. I didn't finish making my list here, though. So then another one is N5. But the one that we're interested in is ZAR. This is the one recommended by Arlo here at Salk, and it's sort of a cutting edge, sort of new type of technology. But they all kind of function the same. And there's one that's been around for decades called HDF5 that performs a similar function and lets you do all of these same things, but it's just so outdated. And then the metadata. Containers use these compressors. So before I show you, before I run my script, I'm just going to show you a little bit of the benchmarking that we did for which compressor is going to be fastest. And we can repeat this analysis. And this was just for writing to the ZAR. So basically copying your images from a directory on your laptop into the ZAR container, which is another directory, as I explained. So we did some benchmarking.
What does ZAR mean?
What does it stand for? Good question.
Well, you don't have to answer it now. I'm just curious.
I don't know. I don't actually know.
It sounds like something from science fiction.
Well, the Z, I can tell you the Z stands for Z-stack.
Zip.
Oh,
No,
Z-array. Z-stack array. Z-stack array, it's got to be.
Yeah.
Okay.
I'm not sure if it's Z-stack because R can be multi-dimensional and dimensional, right? Z kind of suggests it's three-dimensional. I'm not sure what sense of all this.
Yeah, you can work with in dimensions. So, yeah. So anyways, I benchmarked some different compressors for, like I said, just the writing operation, and so we have the ability to benchmark these things. In these preliminary tests, it seemed like Z standard was the fastest. I'm not sure if these results can be relied upon though, because I didn't notice until after the fact that even though it was saying that it was finishing, I wasn't able to actually use the viewer when they were compressed in this manner. So I think my script by default right now is using gzip. So so that's something we'll want to do, is figure out the fastest compressor. So the script I'm going to demonstrate right now, it's going to do these things. The only thing it's not going to do is generate the scale hierarchy. At Genelia on the East Coast, where they're working with NeuroGlancer quite a bit and putting some of their code online, they've got some code for doing this, but I haven't integrated that, and I haven't implemented that code yet. So what we're going to do here, this code is going to take the raw image stack. We're going to point the script at a directory that's just got a stack of TIFF images. In this case, they're just already aligned. Oh yeah, and then of course the alignment isn't connected yet. So right now they're already aligned. We haven't connected it to Art's Swift IR code. So we're gonna write the raw image stack into a numpy array. A target directory is created parallel to the source directory, and that's where the container will live. The data gets chunked and compressed. It's not going to be scaled today. And then we're going to start a local host web server. The directory, we're going to assign it to be served. We're going to instantiate a NeuroGlancer viewer object, which knows where the images are. And then we're going to view that through our local browser. And then we can also, if we wanted to, the NeuroGlancer client code, like the code that knows what a NeuroGlancer viewer is, that can run. That doesn't have to be running on my computer. You can actually, there's one for demonstrate the client side. I don't want to confuse people, but the client side NeuroGlancer code can be running on any machine anywhere, because once you've got and this is all done through JSON. So like the state of whatever you're looking at is all, it's easily transmissible because it's all being done through JSON. And once you can represent a like anything with JSON, it's just really good for being easily transmissible. And so I hope that makes sense. So let's do that then. So let me back out of this and go to a full window view. How are we on time? Not only are these images already aligned to the image stack that I'm using here, it's also a bridged stack, so it's only, I think, 15 or 20 images. So it spits out these links. This is going to use this is going to be the local host viewer. So this is just kind of proof of concept that for how we can start to configure the viewer. These are obviously all the same. This is going to be the three-dimensional view here. And I haven't really got this all totally worked out yet. But
Joel, you're working in the same environment that SWiFT is working in, right? Basically.
what do you mean by environment?
Well, you're both in the NeuroGlancer
Yeah. So we
environment
both,
where you could, your stuff could talk to her stuff as soon as she gets it written. Is that right?
my stuff could talk. You mean my
In other words,
agree with her code?
her trace could be laid on top of the images that you have here as she's working with it, right?
Not at the same time. Do you mean like would our browsers be in sync kind of thing?
No,
I'm not sure I follow what you're saying.
that her tracing will operate on images like this, and yes, that's the next step for us. Mhm.
That's right. Okay, so what you've done, which looks great, is that you've basically replicated what Tom and Art and what Bob had done with them before as a standalone is now operating within NeuroGlancer, correct?
Yeah, just the look.
Just the look so far.
Right. Yeah. And next steps are to now, design some functions and buttons, right, to carry out the procedures. I'm thinking that it won't be too hard for Joel to keep working on this and get it and connect it up to the rest of the Python code. And so that could be happening in parallel with us working on the paper. And probably when the paper is coming out, we'll have this, a prototype of this, or a good beta test version of this working.
Yeah, that would be fantastic, because then right from the beginning, it begins to see its user base expand to all those people who use NeuroGlancer.
Right. And Joel didn't point out, but one of the main reasons for needing to do this is because of the poor performance of displaying the large scale 1 images in QT. And
that's what the GUI is using right now.
Yeah, QT is what the GUI is using right now. This Python technology called, it's actually it's a GUI technology called QT.
Yes. So generating the scale hierarchy is actually useful for two things. It helps with the alignment itself. It's actually used in the process of alignment, but also it's used for viewing. So when you're jumping through, when you're zooming in, when you're zooming into an image, it's at a certain point you might want to just use a lower scale of the image. Or I guess it would be
other way around. You'd want a higher resolution as you zoom in. Mm-hmm.
Yeah. But then and also you only want the chunks that from that image. So you're traversing image scales. You're also, as you move in a 2-dimensional plane, you're moving to different chunks, and you're only being served the chunks that you want when you need them. And that's the technology that underpins, Google Earth, as Thomas mentioned before, right. And here too with NeuroGlancer.
Yeah, and the image display in QT doesn't have that capability. So
Is that right? Mm-hmm.
But yeah. So this is why we don't have good performance when we have the scale 1 images in QT. In alignEM-SWiFT. And the team has complained that when they go to the scale 1, they can't really
scroll through.
They can't scroll through, right? That problem goes away when we have NeuroGlancer.
That's fantastic. That's great.
At our fingertips, yeah. Yeah. And then this question of metadata that Joel mentioned, and I'll point out that some of the team members, I think Lindsay and Masa, have pointed out that that right now in alignEM-SWiFT, your JSON project file is separate from your images. They usually keep them together side by side, but they're actually separate, and you could easily mix things up and mess things up. But when we go to this new technology with the ZAR format, what we're anticipating that we're going to do is to put the JSON project file inside the ZAR as metadata. So it'll all be together. And a question arises, and I think this question applies to the Reconstruct Plus as well. The question is whether or not the ZAR format or the containerized format could take the place and supplant your original raw image data. If it doesn't, then you'll have 2 copies of your data. One copy that's plain TIFFs or something, and another copy that's your ZAR that you're working with in Reconstruct Plus or alignEM-SWiFT. But if we had,
Sorry to interject there. I think we don't want to replace the raw images. We want to keep the raw images and just apply the transforms within Reconstruct Plus, whatever we're using.
But what I'm getting at here is that the raw images will be inside the ZAR. They'll be untouched. They'll be untouched and inside the ZAR.
When it comes time to publish, usually you want to be working with that raw image as the, because once you start transforming things, you get, the image is just not as good as the original raw image, you know? So the question is, will it be easy to capture to take out one raw image that's going to be your demonstrative EM from the
This is
ZAR?
lossless compression.
Pardon me?
It's lossless compression.
So the images are in the ZAR file, and they're compressed in a lossless way, if they're compressed at all, right? You don't have to compress
But I
them.
mean, but you don't.
And it's easy. It'll be very easy to extract any image and bring it out back to your desktop again if you want to work with it that way. Yeah.
Okay. And I that's just a necessary function, but I don't see it as a necessary function to have multiple copies of images.
Right.
Despite the fact that we always do, people always do.
Yeah.
Well, if I, Kristen, this is John here.
Hi, John.
If I may jump in, it's sort of like just a far more streamlined way of what we do now, in the sense that we have a set of raw images and we align them. And right now we save a set of another set of aligned images.
No, we don't. No, we don't.
Well,
No, we don't. We save the raw images with the transform. In Reconstruct, it's looking at the raw.
No, I'm saying
most people are still looking at an aligned version of that image in Reconstruct. I think the only people I think Michael and I are the only ones using the applied transforms in Reconstruct at this point.
Yeah.
Well,
So
all the images that I'm working with were not pre-aligned. But that's from old stuff that was aligned in Reconstruct, and so it was the transform is what's being applied, not an alignment from TrackEM or alignment from SWiFT or someplace else applied to the images. It's the raw image. Some people have images that were aligned in earlier versions of things that were then the alignment was applied to the image, and then the image is brought into Reconstruct and further transformed as necessary. But
Well,
that's what we're trying to get away from.
right. Well, I'm not saying that's the way it should be done.
No.
I'm saying it's analogous, but in a much better way. Like TrackEM makes a set of scale images that we call the mipmap images. And so we ended up like multiple copies of files and an alignment set and a mipmap set. And I think they're saying that something like scale images are exactly like mipmap sets for viewing. And
Yes, that's correct.
And so this new process will sort of imitate what we've been doing manually, but do it in a much more streamlined way.
Yeah. All inside this ZAR container.